Welcome back to the next video, everybody. Today we're going to continue on proving Proposition 5. We'll call this video Proposition 5 Part 2. Let's get into it. We're trying to prove the following, which we called Proposition 5. Let Q be a finite set of primes with those usual properties we've been dealing with over the last couple of videos. Then the Hecke algebra T sub Q is a free O bracket delta Q module, where the module structure is inherited from the structure on RQ via the map phi Q from RQ to TQ that we're trying to show as an isomorphism. So, we're going to begin by considering the action of the Hecke operators on the full space M2 gamma, the space of modular forms, at some level n. Recall that by Riemann-Roch, the dimension of M2 gamma is G plus S minus 1, where G is the genus of the modular curve X gamma, and S is the number of curves of X sub gamma, so we can go back to Chapter 3 to learn about this kind of stuff. You can also see Diamond M modular forms and modular curves 12.1, for example. We'll let tilde T sub O denote the subring of T sub O, generated by the Hecke operators T sub P for P not dividing n, and the diamond operators bracket D for D and Z mod n Z cross. So definition, we'll say that a maximal ideal n of tilde T sub O is Eisenstein if T sub P is like P plus 1 mod n for all P that are 1 mod n. If M is a maximal ideal of T sub O, we'll denote by M tilde its preimage in T tilde sub O. Okay. So why do we like these? Well, what we really like is these non-Eisenstein maximal ideals because of the following result that I'll call lemma rho sub m, which says if L is an odd prime, then the representation rho sub m from GQ to GL2 of T sub O mod m from video 11.10 is absolutely irreducible, which we like because then we can play around with lifting and universal deformation rings, if and only if tilde m is not Eisenstein. Okay, so let's prove this quickly. First of all, if rho sub m is not absolutely irreducible, then rho sub m is equivalent to, let's say, chi1 plus chi2, where n is divisible by the product of the conductors of the characters chi1 and chi2. If L doesn't divide n, then one of the characters is unramified at L, while the other restricts to the cyclotomic character epsilon on inertia at L. This implies that tilde m is Eisenstein, so that's one direction. Conversely, if tilde m is Eisenstein, then rho m restricted to the Galois group of Q adjoin zeta sub nl, so this is an nth root of unity, has trivial semi-simplification. For example, you can see proposition 2.6 in Diamond-Darman-Taylor for that. But this just implies that rho m is reducible. Okay. So, that's the proof of that. So let's keep going. Let's let sigma be a finite set of primes P contained in sigma of rho bar, so that's a throwback definition from last chapter, minus the prime L, such that rho bar of Frobenius at P has eigenvalues, let's call them alpha P and beta P in my field K I'm working with, satisfying the fact that their quotient is not P to the plus or minus first, or equivalently and maybe more enlighteningly, trace of rho bar of Frobenius at P squared isn't just P plus 1 squared. Let's let Q denote the set of primes, little q in sigma, such that Q is 1 mod L. Then Q certainly is then of a set of primes of the type that we've been interested recently over the course of this chapter. Okay, this is one of the two conditions, and the other one follows from this. Okay. Let's also assume that sigma contains a prime P bigger than 3, such that P isn't 1 mod L. Let's let gamma denote gamma not n empty set intersect gamma 1 m, and let's let gamma prime denote gamma not n empty set intersect gamma hm, where n empty set was defined in video 11.12. H is the L-CeLO subgroup of Z mod M Z cross, and then really I just have to tell you what M is now. It's the product over primes P that are in sigma but not in Q of P squared, times the product of primes Q that are in Q. And then let's let X and X prime denote the modular curves associated to these congruent subgroups gamma and gamma prime. Okay? Let's first consider the case where L doesn't divide n empty set. Then, it turns out, X has a smooth proper model, I guess like fancy X, over Z bracket 1 over n empty set M, such that the complement of the cusps parameterizes cyclic isogenies E1 I1 to E2 I2 of degree n empty set, where EJ in this case is an elliptic curve, and IJ is an embedding of the mth roots of unity into EJ. This is all discussed in, for example, Deligne-Rappaport, or in Katz-Maser, as usual. That's where you get all this integral model stuff. The action of H extends to an action on the action of H on X extends to an action on fancy X, and the quotient fancy X prime, which is fancy X mod H, is also has a smooth model over Z adjoin 1 over n empty set M for X prime. The natural projection fancy X to fancy X prime is readily checked to be étal. Okay, so we have to do a little bit of algebraic geometry here, but we're kind of headed towards using differentials to solve the problem. That's what's going on. Okay. So let's let A be a Z bracket 1 over n empty set M algebra, and let's make the following definitions. We'll let omega A be H0, fancy x sub A, omega 1, fancy x sub A over A. We'll let omega prime A be H0, fancy x prime sub A, and then omega 1, fancy x prime sub A over A. We'll let omega tilde A be H0, fancy x A, omega 1, fancy x sub A over A, kind of parentheses D, which I'll explain in a second. And then omega tilde prime sub A will be the analogous definition, with fancy x's here replaced by fancy x primes. Okay, what is D and D prime? So D, like fancy D here, and respectively fancy D prime, this is the reduced divisor defined by the cusps of fancy x, respectively of fancy x prime. So, these might be complicated looking objects, but by the Q expansion principle, which we covered back in chapter 3, we can really just identify these with S2 gamma A, S2 gamma prime A, so spaces of cusp forms, M2 gamma A, and M2 gamma prime A, spaces of modular forms. This means that the first two are T sub A modules, and all of them are T tilde sub A modules. Okay, so these are like higher brow ways to think of spaces of modular and cusp forms over A, in terms of algebraic geometry and sections and differentials and things like that. Okay, so lemma omega, suppose that the A from above is either little k or big K. So either the residue field we're working with or the field of fractions of O. Then omega tilde sub O tensored up to A over O is nothing but omega tilde sub A. Omega prime tilde sub O tensored up to A from O is omega tilde prime sub A. So I don't think that's too big of a shocker. The natural map from fancy x to fancy x prime induces an isomorphism, omega tilde prime sub A with omega tilde h sub A. Okay, so this is like the corresponding sheaf of differentials associated to the modular curve given by h. If n is a non-Eisenstein maximal ideal of T tilde sub O, then the localization at n of the map omega sub O to omega tilde sub O is actually an isomorphism. So once you localize here at n, you get an isomorphism. Finally, if m is a maximal ideal of T sub A, then the m annihilator of omega sub A is one-dimensional over T sub A mod m. Okay, and actually none of these are hard to prove. For example, you could see DDT, page 121. The first guy uses Serre duality. The second guy uses the fact that, which we talked about a second ago, that the map fancy x to fancy x tilde is a tall. The third is a direct check. And the last one uses the identifications, omega A with S2 gamma A with homomorphisms from T sub A to A, which we already know about from above and from previous videos. Okay, so there's not too much depth to this. Let's continue talking about differentials. We were just looking at the case where L doesn't divide an empty set. What about the case where L does divide an empty set? This time X has a regular model fancy X over Z bracket L over an empty set M with the same moduli theoretic description as before. This model is smooth over Z bracket 1 over N empty set M, but fancy X over F sub L has two smooth irreducible components this time crossing at ordinary double points. The quotient fancy X prime, which is still fancy X mod H, is a regular model of X prime over Z bracket L over N empty set M, and fancy X to fancy X prime is a tall still. Given a Z bracket L over an empty set M algebra A, define omega prime A, omega tilde A, and omega tilde prime A just as before, except this time you're going to replace omega 1 by the sheaf of regular differentials. Okay. While the formation of these modules does commute with base change, these can no longer, in this case, be identified with the nice spaces of cusp forms and modular forms that we had before if L isn't invertible in A. Okay. So, for every such A, there is a natural action of the Hecke algebra T sub A, respectively T tilde sub A, on omega A and omega prime A, respectively on omega tilde sub A and omega tilde prime sub A. Why? Well, for the T sub A case, this follows by identifying omega A, respectively omega prime A, with the cotangent space at the origin of the neuron model of A over the Jacobian of X, respectively of X prime. What about in the T tilde sub A case? You need Grothendieck-Serre duality for this. Okay, so if you want some references, you can look at Deligne, Rappaport, Katz-Mazur. You should also, and I've been saying this for a while, you should also definitely read Mazur's Eisenstein ideal paper. Probably the whole thing, but in particular for this talk, section 2.6. And also another good reference would be Mazur-Ribbit, two-dimensional representations in the arithmetic of modular curves, at least section 7, but again, that's another paper you probably should just read at some point. Okay, so this video is just kind of a bunch of lemmas en route to proving proposition 5. We'll do one more for today. So we'll call this lemma omega 2. It says if L is a prime dividing an empty set, then lemma omega from above carries over with all the above notation and the additional hypothesis that T sub L is not an M for part D. Okay. So in other words, up here we still have the same results with some mild changes, even in the case L divides an empty set. And what are the changes? They're listed down here. Okay. And in fact, the proof is more or less the same as lemma omega. Part D is a little bit more delicate. But it turns out you don't actually need to prove part D in full generality, because we only ever apply it to the case rho sub M is not a good representation. So we can actually just mimic an argument given in Maser-Ribet's paper, two-dimensional representations in the arithmetic of modular curves. I mentioned this paper above, specifically proposition 20 there. You can kind of mimic an argument given there to produce part D in an easier way than it would be to prove part D in full generality. Okay, so we got a couple like lemmas out of the way, and so we'll just keep pushing towards proposition 5 next time. Thanks for watching, and I'll see you then.